Welcome to our review of geometric optics. In this video, we'll cover the fundamental principles that describe how light interacts with different optical elements. Whether you're studying for an exam or just curious about how lenses and mirrors work, this comprehensive review will help strengthen your understanding of this fascinating topic. Let's start by discussing the nature of light. In geometric optics, we treat light as rays that travel in straight lines. These rays propagate outward from a light source and continue in straight lines until they interact with matter, such as mirrors or lenses. Now, let's move on to reflection. When light encounters a reflective surface like a mirror, it bounces off, following a predictable pattern. The law of reflection states that the angle of incidence equals the angle of reflection, both measured from the normal to the surface. The normal is an imaginary line perpendicular to the surface at the point where light hits it. Mathematically, the law of reflection can be written as theta I equals theta r, where theta I is the angle of incidence and theta r is the angle of reflection. Next, let's discuss refraction. When light passes from one medium to another, like from air to water, it changes direction. This phenomenon is described by Snell's law, which states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction equals the ratio of the refractive indices of the two media. For example, when light moves from air into water, it bends toward the normal because water has a higher refractive index than air. Related to refraction is the phenomenon of total internal reflection. When light attempts to move from a medium with a higher refractive index to one with a lower refractive index, like from water to air, it can be completely reflected if the angle of incidence exceeds what we call the critical angle. The critical angle is the angle of incidence that would cause the angle of refraction to be 90 degrees. You can calculate the critical angle using Snell's law by setting the refraction angle to 90 degrees. Now, let's talk about lenses which use refraction to focus or spread out light. There are two main types of lenses, convex and concave. A convex lens, thicker in the middle than at the edges, converges light rays that pass through it. A concave lens, thicker at the edges than in the middle, diverges light rays that pass through it. Let's discuss the lens equation, which relates the image distance s prime, the object distance s, and the focal length f. The lens equation is given by 1 over s plus 1 over s prime equals 1 over f. We can also define the magnification of the lens, which is the ratio of the image height to the object height, and equals negative s prime over s. Now, let's talk about mirrors. There are two main types of mirrors, concave and convex mirrors. A concave mirror, which curves inward, can converge light rays to form a real image if the object is beyond the focal point. A convex mirror, which curves outward, always forms a virtual, upright, and reduced image. Just like with lenses, mirrors also follow a similar equation known as the mirror equation. The mirror equation is 1 over s plus 1 over s prime equals 1 over f, where f is the focal length, s is the object distance, and s prime is the image distance. The magnification is given by m equals negative s prime over s, which is the same as for lenses. Let's briefly discuss sign conventions in geometric optics. For both lenses and mirrors, we typically use the following sign conventions. Distances measured in the direction of incoming light are positive. Distances measured against the direction of incoming light are negative. Heights measured upward from the optical axis are positive, while those measured downward are negative. A positive focal length indicates a converging optical element, while a negative focal length indicates a diverging optical element. Finally, let's briefly discuss some common optical instruments. Cameras use convex lenses to form real, inverted images on photographic film or digital sensors. Microscopes use multiple convex lenses to magnify tiny objects. Telescopes can use lenses, mirrors, or a combination of both to observe distant objects. These instruments rely on the principles of geometric optics that we've covered throughout this video. Let's summarize what we've learned in this geometric optics review. We've covered light rays, reflection and its laws, refraction and Snell's law, total internal reflection, lenses and mirrors, as well as their equations and magnification formulas, sign conventions, and optical instruments. Remember, geometric optics is all about tracing rays and using simple mathematical relationships to predict how light behaves as it interacts with mirrors, lenses, and other optical elements. Thank you for watching this comprehensive review of geometric optics.